Flipped classroom video for Maths AS Unit 2, the constant acceleration equations, Part 2. Now, we saw how the equations of constant acceleration were developed in the last presentation, and you can either use the S for displacement or X for displacement, and we'll have both in this presentation. Now, example 1. A particle accelerates steadily from rest, so pause there, at 1.4 meters a second squared. Find its speed after 8 seconds. So let's do that first. Let's see what information we know. So, a quick list showing the known values of A, U, T, V, and S, and the values to be calculated and the values that have no interest to us can often help in deciding which equation to use. We'll use a question mark to indicate values to be calculated and a cross to indicate values that are of no interest to us at all. So in this part of the question, we have A was 1.4. It's starting from rest, so U is 0. Its speed after 8 seconds, so T is 8. We don't know V, but we need to find it. And S, we don't know, and we don't need to find it in this part of the equation. So the equation of constant acceleration that does not use S is V equals U plus AT. So putting that down, putting values in, we get that V is equal to 0 plus 1.4 times 8, and that gives us 11.2 meters a second. So that's the first part of this question. Part B, we need to find the distance it has travelled by the time its speed reaches 25 meters per second. Two ways of denoting meters per second, either meters divided by seconds or meters S to the minus 1. Both forms of the unit mean the same. So B, what do we know? So A is 1.4, it's the same for all parts of the question. U is 0, starting from rest. T, we don't know and we don't want to find. V now is 25, so when the speed reaches 25, so V is equal to 25, and S is what we want to find, the distance it has travelled. Sometimes the distance it has travelled and the displacement are not the same, so be careful. This is going in steadily from rest, so it should be the same. So S is going to be what we want to find. So which equation does not use T? Well, it's this one. V squared equals U squared plus 2AS. It might be useful for you to write down, if you see an equation of motion question, for you to write down the equations of motion at the side of your paper so you can see quickly which one you want. So putting values in here, we got 25 squared is equal to 0 squared plus 2 times 1.4 times the S we want to find. So 625 is equal to 2.8 S divided by 2.8, and we get S is equal to 223.2 meters. So part C now then, the time he takes to travel 280 meters. So this time, what do we know? A and U were given at the beginning. T is what we want to find, and S is 280 meters. So V is the one I don't know and I don't want. So an equation not involving V is this one. So S is equal to UT plus a half AT squared. So S is 280, U was 0, plus a half times 1.4 times T squared. Now, being as we've got a naught there, it's only a quadratic without the T term, so it's just T squared we've got in the equation. We can divide by 0.7 and we get that T squared is 400, so T would be plus or minus, but in this situation, we're taking the positive, so t is 20 seconds. Example 2. The brakes on a train produce a constant retardation of 0.375 meters a second squared. Now, retardation is slowing down, so it's got a negative acceleration. So we'll be using a equals minus 0.375 for that question. Find the time to stop from a velocity of 54 kilometers an hour. Now, kilometers an hour, we aren't allowed to use. We have to use the SI units, so we'll need to change that. So earlier we observed that if the velocity and acceleration of an object have the same sign, are in the same direction, that is, then the speed of the object increases if they have different signs. If they're in opposite, but if they have different signs, that is, they're in opposite directions, and the speed of the object decreases. The velocity and acceleration of the braking train must therefore be opposite direction. So the train is moving forward at 54 kilometers an hour. It's being retarded, so being slowed down by, and then, so the retardation is going in the opposite direction of the motion. Positive direction is from left to right. So our acceleration will be a minus. But we need to change the kilometers an hour. So we need to multiply by 1,000 and divide by 60 and another 60 to get seconds. And that gives us 15 meters per second, which we are now allowed to use. So what do we know? So A, our acceleration is going in a negative direction, so minus 0.375. U is 15 meters per second. The time to stop, so that's V, would be 0, and we want the time. S we don't want and we're not interested in. So which equation uses these four values? Well, it's this one. So V equals U plus AT. So 0 for V is 15 for U plus minus 0.375 times T. T is the only unknown. So we can rearrange and we can find that T is 40 seconds. So 40 seconds to stop. Part B. The distance required to stop from a velocity of 90 kilometers an hour. So 90 kilometers an hour we have to change again. Therefore 90 kilometers an hour multiply by 1,000 divide by 3,600 and we get 25 meters a second. So it's going to start at 25 meters per second. Our acceleration is the same retardation, so minus 0.375. Distance required to stop, so V is 0. T, I don't want and I don't need to find, and I'm not interested in. Therefore, I can ignore T, and I need to find S. Therefore, which equation do I need? Well, the one not using T is this one. So putting values in, we've got 0 squared is 25 squared plus 2 times minus 0.375 times the S. Rearranging, and we get S to be 833.3 meters. So the distance to stop would be that. Example 3. A car passes a lamppost travelling at 15 meters a second with constant acceleration of 0.75 meters a second squared. 336 meters further down the road, the car passes a second lamppost. How long does it take the car to travel between the two lampposts? So what do we know? Well, let's draw a diagram and see what we know. So at the beginning, it's travelling at 15 meters per second and it's got an acceleration of 0.75. Between the two lampposts, we've got 336 meters. So A was 0.75, U was 15, V we don't know and we don't want, T we need to find, how long does it take, and S is 336. Therefore, the equation that does not use V is this one. So S is ut plus a half at squared. Putting in values, 336 is 15 times t plus 0.375 times t squared. Now we have now a quadratic in t. So we need to get the terms in order and equal to 0. And either use a formula or your calculator and you get t is equal to 16 or minus 56. We don't want the minus time, so we've got t is equal to 16 seconds to travel between the two lampposts. Example 4. A particle moves along the x-axis with constant acceleration. Initially, the particle is at the point 0, 0, and 2 seconds later, the particle is at the point 10, 0. A further 4 seconds later, the particle is at the point 24, 0. Determine the initial velocity of the particle and its acceleration and deduce when and where the particle is stationary. So we're moving in a straight line. At time t equals 0, it's at the point 0. It's moving with velocity u and it's got acceleration a. At the point t is 2, we're at the point 10, 0. So what do we know? So a we don't know. We need to find its acceleration and its velocity. So we need those two. X at the moment, v at the moment we don't need, so put a cross there. T is 2 seconds to get to the point where x, and we're using x now instead of s. It doesn't matter what you use, but we'll use x in this question instead of s. So x is 10. So equation we need would be this one, which does not include v. So putting values in, we get 10 is equal to 2 u plus 2. 2 squared divided by 2 is 2a. So we've got an equation with two unknowns, but we've got another situation, so we're going to call that equation 1. So when t is 6, so 4 seconds later, instead of using between 10 and 24, we're going to use from 0 to 24 because we need to find its initial velocity. So between 0 and 24 is taken 6 seconds. So putting those values in, still need to find a and u. V we don't want. T is 6 and x is 24. So equation, the same equation we're going to use, putting values in. So 24 is equal to 6u plus 6 squared divided by 2 is 18a. So we have two equations. So we have two equations. You could have divided the first one by 2 and the second one by 6 to make it easier. But solving those whichever way you want, and you get that u is 5.5 and that a is minus 0.5. So we're slowing down. So particle is stationary when v is not. So we've worked out the initial velocity and the acceleration, deduce when and where the particle is stationary. So stationary when v is equal to 0. So using an equation with v equals u plus at, and we get 0 equals 5.5 minus 0.5 times t, rearranging, and we get t is equal to 11. So t is 11. We need x, when it's when and where. So we've done the when. The where using x is ut plus a half at squared. We get 5.5 times 11 plus a half times minus 0.5 times 11 squared, and that works out to be 30.25 meters. So particle is stationary when t is 11, and it's at the point 30.25, 0. Another example, A and B are 2 points 200 meters apart on a stationary line. A particle, P, starts from A with initial velocity 3 meters a second, directed towards B, and travels along a straight line with constant acceleration 1.8 meters a second and directed towards B. 5 seconds later, a second particle Q starts from rest at B and travels along the same line with an acceleration of 2.4 meters per second squared, directed towards A. Determine when and where the two particles collide. So we've got two situations. So we're going to have simultaneous equations again. So setting up the scenario, so 200 meters between A and B. P travels from A. So that's the displacement of P, S of P, and it's traveling at an acceleration of 1.8. It's got initial velocity of 3 as well. B starts from rest, so that starts at U is 0. It's got an acceleration towards A now of 2.4. And its displacement we're going to call SQ. And then when SP and SQ add up to 200, they should collide. When P has been traveling for t seconds, that equation gives SP is equal to 3t, 3 was its initial velocity, plus a half A is 1.8 times t squared. So we have S of P is 3t plus 0.9 t squared. So that's first equation. Q will have been traveling for t minus 5. It starts 5 seconds later. And so I'm taking positive for B to be from right to left. So SQ would be 0. So 0 is U. T minus 5, so that's going to be 0. Plus a half times T2.4 for the acceleration times T minus 5 all squared. So SQ is that expression. The collision occurs when SP and SQ add up to 200. So SP was 3t plus 0.9 t squared. SQ was 1.2 t minus 5 all squared. That should add up to 200. So multiplying the bracket out, collecting terms. So we've got t squared being 2.1. Then we've got minus 10t times 1.2. Add a 3 gives us a minus 90. And then we've got plus 30, 200 the other side, bring it over. And we get a quadratic now in t, 2.1 t squared minus 9t minus 170. Put it into your calculator and get values of t of 11.39 or minus 7.11. So we don't want a minus value. So t is 11.39. Where? So putting that value back into SP, displacement of P, you could have put it back into either. And we get a value of 151, but we can then say it's from A. So collision occurs when t is 11.45 and occurs at the point 151 away from A. If you put it into this equation, the t, you'd get it away from B. And that's the end of that presentation, giving you examples of using constant acceleration equations.